Okay, welcome back. We're on page 153 telling you that this is an example of a grammar, a set of rules that say sentences have this, and nouns have this part, and verbs have these, and here's what the acceptable articles are: adjectives, nouns, adverbs, and verbs. Okay? That's how it kind of sort of works. So obviously this is simplified because we have a heck of a lot more than that, but you see how this thing works. So grammar structure is the formal language grammar, which provides this type of structure. You can use this to test to see if a word exists, right? If I say tree, well, let's just go through. Is tree part of that? Nope, not in there. Or I could come up and say, is this valid structure? So tall tree, well, okay. A tall car, is that valid? Yes, it is. So it can tell you, does a word exist, and it can tell you if it matches the grammar. Okay, so it's kind of like spell check kind of a thing, right? Does the word exist, and then is the context of the word correct? Okay. So on page 154, they get a little bit crazier and start talking about this thing where it's recursion. So some sort of a sentence, and I could have like a letter A, and then I could start this guy over, and so I'm like surrounded by A, and then I'm surrounded by B, and then I'm nothing. So what this basically means is a sentence could have something surrounded by A, or a sentence surrounded by B, or it could have nothing surrounding it. So this is kind of, now think about this. Let's just envision this back to our example. What if A was a space character? Ooh. And B was a tab character. Ooh. Now this is making a little bit more sense now. A sentence could be something separated by spaces, or something separated by tabs, or something all by itself. See how this little language thing kind of works? Okay, good. On page 157, they talk about a finite automatons, or automata, plural. I know, it's crazy. So this is the simplest type of abstract machine. It has a finite set of internal states. That would be very helpful. It has an input tape, and has some sort of a transition function. And so, one more time. You process one symbol at a time. You can't fast forward, you can't go backwards. And so finite means I'm always going to get one answer. And so if the task for my finite automaton is to say, is a word in the language, okay, if that's my task, I'll just run through this, and the answer is going to be yes or no, right? That's all there is. Cool. So on page 158, they give an example of one. So states and transitions. Okay, I know it's a little weird. So if I'm in state 1 and I want to get to state 2, then I have to go through A to be able to get there. And then I could get back to 1. But if I want to get to 4, I can go to B. Now, is that the only way to get to 4? Well, no, I could use B and then A and So I'm not so certain how helpful this diagram is in describing state transitions. But yes, you have particular states, like am I inside a word, am I not inside a word, and then you have transitions that take you there. Sometimes they're just one way in, and sometimes they're not. And so a regular language means it can be accepted by a finite automaton. But it has a regular expression, which means I can always find something. It has a grammar. So those are the 3 rules for coming up with what's called a regular language. Okay. Regular expression, one more time. I'm going to defer an awful lot of that because we're going to do practical examples in the next lecture, not philosophical examples that are in here. All right, one more time. Deterministic versus non-deterministic on page 163. This one basically says every stage has only one edge leaving it. In other words, only one way out. Okay? And so this one there's two ways out of this guy. I can go back this way and go back that way. So in other words, it allows looping. So non-deterministic, or I'm sorry, deterministic, yes, non-deterministic. In other words, do you allow more than one edge coming off of something? In other words, does it allow looping? Okay. On page 164, they finally start talking about coding. Thank you. Where this is a generic scenario where I have some sort of state, and then while I'm reading my symbols, I check to have a switched statement, and I figure out what it is I'm supposed to do. And then at the very end, I go, wait, whoa. Do I still have something? And then not. This is identical. If you look at this, that's identical to what I've got here. I mean, I'm reading these words one at a time. Have a case statement that looks for 3 different types of white space, and then everything else that's not white space. So I'm maintaining state of, am I in a string of white space, or am I in a string of real characters? And if so, I need to do something. That's exactly what this guy does. Whoa, not that guy. That's exactly what this guy does. It's just that. Now, on the next page, on page 165, they show an example that's kind of sort of similar to mine. I just kind of like mine better because I can demo the dang thing. Okay? Good. Phew. All right, so one more time. Let's just envision this is, instead of doing it by white space, I want to get back to this thing where I want to count the number of sentences. Wow. How complicated is that? Man. Is this going to be one of those things that has a bunch of loops in it? Yeah. I can tell you right now, this is probably going to push that on the stack and then calculate that separately. Right? This is going to have a lot of stuff to do. So, what are the end of sentence symbols? Can those symbols be used in some other context? Yeah. What happens if things are quoted? Yeah. So this pseudocode here is perfectly okay in the one on page 165, but this basically tells you this is how you're going to have to do that. Now, I would have to have multiple states here. Like, what's the context of this dot? Or what's the context of, a quote? Am I inside a set of quotes? Right? It'd be an awful lot of stuff you had to do. Okay, moving on. On page 167, they talk about designing finite automatons. I'm going to skip that entire section. Okay, just saying. And let's get to the good part on page 174, where I talk about what are the restrictions of doing this technique. So I'm assuming I built one of these things. What can it do? Well, first of all, if you go back to this example way back here, I mean, this could go on forever, right? So I basically have to have a limit, a manual limit that says, no. We're never going to have more than 5 or whatever the number is. Pick a number. So one of the limitations of this is there's a finite word length, okay? And the other limitation is I really can't do matching. I can't do like pattern matching. Is A asterisk in the library, in the language. I can't do that. That's what regular expression things are for. Okay. So I'm going to skip the rest of this. I just wanted you to hit that. What are the equivalence and limitations sections is just about, what I have to have a fixed length and it doesn't do pattern matching. Cool. On page 182, they finally start talking about a push-down automaton. Now, in their world, on page 182, I'm using a stack. I chose not to. Okay? Just a choice. I chose not to do that. And I have a housekeeping variable here on 23, which I don't really need, but I kind of like it. And so that's what this is all about. A push-down automaton is something that can store up data and then spit it out at a later time. Okay, so there's 3 parts to this. The current state that we're in, the remaining part of the word, and then the stack contents, which is, right, the previous part of the word. So To see if a word is in, using this technique, to see if a word is in the language, okay, I would check the state, the current state, my input, my previous input, which is in the stack, and then I'd have a transition function that switched between, you know, am I in white space, and then do a compare. So I'm going to skip a bunch of that because I've demoed how that's actually done. And so I don't think we need to beat that too much. So I mentioned, I think, that you have a homework assignment that's going to be doing something very, very similar to this. So you really going to have to think about this and figure out how to transition, how that transition works and how those states work. It's gonna look like this. You're gonna be reading one character at a time, and there's gonna be a switch statement, and there's gonna be some case statements, and you're gonna have to figure out what state you're in. Yes, 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 absolutely, positively. Moving on. Page 187, they talk about context-free grammars. So context-free grammars allow for nesting, right? Because in the real world, I could, instead of having table, I could have something like select asterisk from table, right? I could have some nesting stuff in there. So context-free grammars allow me to have some nesting, and you have a choice on whether you want to work from the outside in or the inside out in the computer world or in doing math. I basically don't really have a choice. I really have to work from the inside out. Right? I have to do the 4 times 2 before I can do the addition. And I have to do this before I can do that. Right? I mean, there's no choice. But in the book, they're saying, well, you know, work from the outside in. I'm thinking, okay, whatever you say, dude. So, this kind of lends itself to something that you might expect to see in HTML. All right? So, here's an HTML document. So, I'm going to say HTML. And then here's a closing tag for HTML. And then I could have something nested inside here, right? I could have a a paragraph statement. This is and then I could have a bold. And then maybe even, I'll throw in an italics. How about this? I'm trying to think of something that makes some sense. Hang on a second. This is a long. Okay. So, I've got this part is wrapped in, so the italics is wrapped inside the bold, which is inside a paragraph, which is inside an HTML. Wow. So yeah, awful lot of nesting going on. Now, is this valid HTML if I was to swap these guys around like this? Where I don't actually behave, the rules don't actually work. Now, to tell you the truth, first of all, this will work. I'm not asking you, does it work? I'm asking you, is this strictly valid HTML? And the answer is no, it is not. Because nesting should always work with beginning and ending tags that match. You can tack on one, but you can't switch them around, okay? So that's one of the rules. That's one of the grammars. Okay, cool. So on page 201, they talk about the limitations of the push-down automaton, but quite frankly, I think we've covered it all. I mean, again, the push-down automaton is very cool for like parsing words and things like that, but it's really not suitable for like doing pattern matching and things of that nature. Okay, doggone it, we're coming up on the 15-minute mark, so we'll finish this thing off in just a few more minutes.